Now we have Luisa talking on PAC learning social networks via threshold-based opinion dynamics.
Well, hello everyone. As Mark said, I'm Luisa, and this is work that we have been working on with Dimitri Chistikov, Mike Patterson, and Paolo Turini. This is fresh out of the oven, so I hope that you enjoy it. So why do we care about studying social networks? Well, I hope everyone here is a human. So one way or another, we're going to be embedded in a social network, and the opinions that we hold for different things are going to depend on different aspects and the people that we are surrounded by. But from a mathematical point of view, we can also model the social networks as directed graphs. And we can say that the nodes in those graphs are going to be our agents, and the edges on those graphs are going to be their influence relations. So for example, if I have my graph and I have an edge connecting agent 1 with agent 2, that means that agent 1 influences agent 2. I also mentioned that we can have opinions. Our agents can have different traits. So for example, I can ask a very pressing issue like, am I going to like the cake after this talk? I can color my nodes as white if I'm going to like it. I can color my agents as black if it's not going to like the cake after this talk. And with that, also we can have different dynamics. Our opinions are not static, so they're going to evolve over time. And because opinions evolve, we can have different questions regarding to this. We can ask which one is going to be the most influential agent that we're going to have in our social network if I want to promote a product. I could also ask, are these opinions going to converge at some point? And as well, I could ask, can I manipulate the agents in my network such that I get some sort of ulterior motive, ulterior behavior on it? This is kind of like the usual framework that we have, but what we see in literature is that they always assume that we know the graph and we know these influence relations. What we propose is, well, what happens when we don't know which ones are these influence relations? What can we say about the underlying structure just from the opinion diffusion? However, we're not going to be too greedy. We don't need to find exactly what is going to be the graph that we're working with. We just need to be good enough. What is this good enough? That is when we have the PAC learning approach or the probably approximately correct learning, where probably and approximately are embedded in these two parameters here, the epsilon and delta. Epsilon gives us an error for this approximately correct. Delta gives us the probability or a confidence. What is our goal? We want to have very high confidence, so with very high probability, whatever we guess to be with a very small error from the actual network that is generating this opinion diffusion. But our problem is going to be ill-posed. What does this mean? It means that if we can observe some opinion diffusion steps, for example, right here, there are going to be multiple networks that can generate this diffusion rule. So for example, if I see my network with 3 agents, and then these 2 change opinion, and this one right here doesn't change opinion, then I can, with this information, I cannot possibly tell that this happened because it was this network that generated that diffusion, or because this agent didn't change opinion just because it didn't care and wasn't connected to the top agents at the top, to the agents at the top. This is where we come into place the consistent hypothesis finder. What are consistent hypothesis finders? They are algorithms that basically just fit to whatever information that we have available. So if I just have one observation, I just need to retrieve something that's consistent with that information and that observation. Next question is, okay, as I start sampling, as I get more opinion diffusions, more opinion steps, I can have more information, less networks are going to be consistent with what I've seen. But how many observations are enough observations? That is something that Shalev Schwartz and Ben David told us. So in 2014, they said that if we have a network with n agents, the number of observations that we need is around this number, this n right here, in order for us to be as close as we want for our PAC learning errors and confidences. If you see, it's kind of like quadratic in the number of examples that we need to get. So where is our goal? Now, our goal is going to be, we want to design a consistent hypothesis finder such that it's polynomial in the number of agents in my social network and the number of examples that I can see. Okay, so in the title we have opinion, threshold-based opinion dynamics. These are going to be the opinion dynamics that we work with. Our opinion dynamics are going to be unanimity, all but kappa, and majority. In unanimity, our agents are going to be very stubborn, which means that only if all their influencers disagree with them, they're going to change opinion. So in this case, they change opinion from black to white. But as soon as one of the influencers agrees with their opinion, then they're going to remain the same. In the all but kappa, we're going to allow that at least kappa of my influencers to agree with me, but I still change my opinion. If I have that parameter kappa, then I will just remain with my current opinion. And then we also have a specific case of this, which is the majority dynamics, which we can think about as peer pressure. I have my influencers, I ask for a vote, and then just simply take the opinion of the strict majority. If there's a tie, then well, I will just remain with the opinion that I had at the beginning, which is this case. For example, in this case, we have 3 people that are telling my agent to change opinion, it's going to change. In this case, 3 people, they're telling them to do not change opinion, so it doesn't change. But this could lead to like some ambiguities. Something that's nice about this is that we can decouple the agents in our social networks. This means that we can just take one target agent, ask which ones could be a feasible set of influencers for my target agent, and then simply run my algorithm in parallel for all the other agents in the network. And with that, we create something that's called a matching transformation. What is the matching transformation? Basically, we have an oracle. The oracle is going to sample a bunch of opinion states in my social network, and it's going to predict if my target node is going to change opinion or not going to change opinion after one step. So let's see, in the first case, let's see, my oracle sampled this opinion state. My target agent has opinion white, and it told me that it did not change opinion. So those agents that are going to match that not changing of opinion are going to be the ones with the same opinion. So the agents with opinion white. What happens if I then sample this opinion state? My agent has opinion white, but my oracle told me that my agent changed opinion. Then those agents that matched that were those with opinion black, with the opposite opinion, telling it to change. And now we can store this information into what we call a matching matrix, which basically is just we put a bunch of ones if they match the oracle prediction, and we take -1 if they didn't match that oracle prediction. But -1s and 1s, they're not very pretty to look at in a presentation, so we're still going to use black and white dots, where if they're white if they match, black if they do not match. And now we get some results for our opinion, threshold-based opinion dynamics. Let's start with unanimity. In unanimity, what we want to do, we want to split our samples between where did the oracle predict that my target node was going to change opinion, where did it predict that it wouldn't change opinion. If my oracle tells that my target node has to change opinion, then it means that all my influencers have to match that prediction because we're in unanimity dynamics. That means that in this case, I just have to see those that always match for this oracle predictions. So in this case, I can just yeet agent 1 and agent 4. Once I have that, I can simplify my matrix, and now I just look at this point. So I just have the remainder labelings that I have for my network, where my oracle said that my target node didn't change opinion. Because we have unanimity, we need to have at least one of my agents always not matching the oracle's prediction. That means that I have to sort of like make a path that will go, I'll always come one path, one agent here, and one agent here. So I can go through all the labelings for it to be consistent. We are going to call this the streams. And eventually the streams are going to create a waterfall, so wait for it. In this case, we know that the agents that form the stream are going to be a feasible set of influencers for my target node. For this case, we have that agent 2 and agent 3. They can be a feasible set of influencers for these observations. But I could also take agents 2 and agent 5. I have a stream. So for both cases, I have that the feasible set of agents 2 and 3, 2 and 5, could be a potential solution for my consistent hypothesis finder. What happens when we complicate things a little bit more? What if we go to the all but kappa dynamics? Once again, we're going to split the oracle's predictions into when does the agent change opinion and when it doesn't change opinion. When it changes opinion, we still have polynomial time, assuming that kappa is a constant value. If you want more details, we can talk afterwards. But what happens is that once we have the dynamics where at some cases my agent is going to change opinion, at some cases my agent is not going to change opinion, then our consistent hypothesis finder they run still with some large polynomial, but still this G could be the actual set of influencers coming from the true social network, which we could get some mild assumptions under the network size. For example, if you have regular graphs or we have some sort of like small world properties going on, we can still remain polynomial, but we're starting to see that we're having troubles into finding like a consistent hypothesis finder in polynomial time. In this case, we go back into a specific case, which is the majority dynamics, which we can model it as a specific case of the all but kappa. And for that, we actually find that there's a related problem called the heat set problem that kind of like looks similar to what we're doing. The heat set problem tells us that if I have a collection of sets and then I have a budget D, I want to find a subset that doesn't have more than D elements, that has a non-empty intersection with all the sets in my subset, in my collection of sets. And that actually we have seen in Rudo 2017 that can translate into if I have a matrix with plus and minus 1 entries, can I check which columns I can pick such that I always have a positive row sum. And if we remember, basically our matching matrices, they're just these type of matrices. And then one could think that, oh, this is great. We have someone that's talking about this problem. We just translate it into our context of social networks. Where's the break? Well, the break is that the hidden set problem is known to be NP complete. Or in other words, the hidden set problem is known to be very hard to solve. Despite this, we came up with a heuristic of how to find a feasible set of influencers for a given set of opinion diffusions. So we call this the waterfall algorithm. We're going to separate our agents between which ones are the agents that we're including into our waterfall and which agents do you want to add next. Then we're going to have a vector that's going to tell us which of our examples are already inconsistent, which ones are potentially inconsistent, and we're going to focus on those. So in this case, we can have those that are already inconsistent, so the ones where our agent doesn't match the oracle prediction. Those that are at risk to be inconsistent are those that if I add another agent that doesn't match my oracle prediction, they're going to become inconsistent. So they wouldn't work as for my consistent hypothesis finder. Then once I have which examples am I looking for, I want to see, okay, how many of these labelings are going to work? How many of these labelings is each agent is going to work with? And we're going to call this the rescuers. So every time that our agent is part of the matching set, there's going to be a rescuer for that labeling. If it's not, then it's not. And then we just want to see which of our agents has the most rescuers. In this case, the agent is agent 5, which has 5 rescuers, for example. So we're going to add it to our waterfall. Once we have this, we want to see how many streams do we have in our waterfall with relation to how many agents we needed to build this waterfall. We actually have a proposition that tells us if we have a good enough ratio, then we know for sure this is going to be a feasible set of influencers, if and only if. In this case, we don't have enough because we still have some inconsistent examples, so this is not consistent yet. So we need to come back to the agents that we haven't picked yet and see which one has the most rescuers. In this case, agent 2. Once we add it, now we have built two streams. And if you see, we have two streams over 3 agents. This proves that at each of the examples, we're always going to have 2 of our agents matching the oracle prediction. In this case, agents 1, 5, and 2 are going to be a feasible set of influencers. So it's great because we have proven also that this heuristic is going to terminate in m times nq, which is polynomial, a small polynomial actually, time. But does it always work? No, it doesn't always work. Otherwise, we'll be saying that p equals a p, and I'm not saying that anymore. We have all been there. But it does have some empirical, like it's kind of like well-behaved in practice. We have shown that we can guarantee to always find a solution for very small networks. We're also guaranteed to find a solution if there's a solution with 1 or 2 agents, just part of this hidden set. And also we are guaranteed to never have false positive. What is a false positive is basically the algorithm telling you this is a feasible set of influencers when in reality it's not a feasible set of influencers. The type of errors that we have are false negatives, where the algorithm tells us there's no feasible influencer set that could attain the opinion diffusion that we have observed, when in reality there was actually like a possible solution. We run this over 60,000 randomly generated networks. In this graph, we can see how many times the algorithm failed in percentage. So we have that none of them surpassed the 28% like error. And we also saw kind of like this region happening here, where if we are above the m, the number of examples, being greater than n squared, the number of agents, then we never failed. And if we are like below this line of n minus 10, we also never failed with our heuristic. And also we see that if we have these bounds and we come like closer to the middle, that is when we're starting to have more problems, which can like also suggest that maybe there's some sort of like parameterized complexity problem, or like our errors depends on these like proportions and this ratio between how many observations we have versus how many agents we have in our network. An intuition could be that when we have enough examples, we're way past our bound, we have well enough information such that there's only one solution, versus for the lower bound means that we have enough agents and not a big enough sample, so many of them are going to match. So we're going to have multiple correct solutions for our algorithm. And so with that, so far, what have we done? We have created like some consistent hypothesis finders for unanimity and all that kappa under some mild conditions. And we have also proved the hardness results for the majority case of our problem. What's coming next? Well, we want to keep testing, like empirical results are cool, but that's not a proof. We also want to come up with like a analytical way of counting these false negatives problems that we have for a waterfall algorithm. Yeah, so that'll be it. That'll be me. Thank you. You know how I put like a timer and then didn't set it up.